Hi, today I would like to present my final report on my topic Hyperloop, which is an efficient, cost-effective, and a cleaner mode of transportation. So, what exactly is the Hyperloop? It is nothing but the brainchild of Elon Musk, and his idea was devised by him in August 2013. The blueprint and the basic design of the idea was created by Musk along with his engineers at SpaceX and Tesla. The underlying model of the Hyperloop works in a way such that a capsule or a train runs inside a tube. The tube is ensured that it is kept at a low pressure environment by ensuring that there is nothing but vacuum in the tube. Due to low aerodynamic friction present inside the tube, the vehicle is accelerated in a forward direction using the concept of magnetic levitation. I know this sounds completely bizarre, and we all must be wondering as to how does it exactly work. So I have a cool slide coming up next to indicate the conceptual design of Hyperloop. We all remember watching the Jetsons when we were kids, wherein one of the persons would go inside a tube, as shown on the left-hand side, be inside the tube for some time, and is floated magically on the other side, from one destination to another. Similarly is the conceptual design of Hyperloop. Instead of a person going directly inside a tube, imagine the person is present inside a train and this train runs inside a tube. Musk recently tweeted that this train or this particular capsule inside the tube can actually run at a speed which is equal to the speed of the sound. I know this sounds completely bizarre, but it's actually achievable. And engineers at SpaceX and Tesla are working in order to achieve such a humongous amount of speed. One of the reasons why I decided to do a thorough system engineering analysis of the Hyperloop mode of transportation is due to the numerous advantages associated with that of Hyperloop. The first one is efficiency. Hyperloop claims that it is the most efficient and quickest mode of transportation available for daily commuters. Let's compare it to the other modes of transportation that are available. How about airplanes? Let's say we want to travel for a distance of 900 miles. Traveling by airplanes is going to be completely unfeasible because half of the time would be wasted in the ascent and the descent of the flight. This is not practical for daily commuters like students or office going people who want to have most possible time efficient as possible. The second mode of transportation is that of railways. The biggest issue associated with railways is that it stops at every destination possible. Thus, let's say in a crowded place on a daily basis, if passengers travel from place A to B, ensuring that they stop at every possible place between A to B is not going to be feasible. And this is what Hyperloop claims is not going to happen with its model. And the third mode of transportation is that of roads. Lots of traffic congestion in big cities like Los Angeles, California, or New York. And traveling by roads is not a better option. All these things will be avoided in Hyperloop, which will look further when you look at the proposed route for Hyperloop. The second advantage is that of cost. The basic design for Hyperloop was created by Musk in order to the reaction of the California high-state railroad networks, which is extremely expensive and has a humongous production cost associated to it. If you look at the production cost for Hyperloop, it cost only 6 billion USD dollars in order to ensure that the entire system is up and running. The third advantage is that of robustness. Since the Hyperloop mode of transport consists of a train traveling inside a tube, passengers who are traveling inside the train will be immune to bad weather conditions such as fog, dust, wind, as well as earthquakes. And the last and the most important advantage is that Hyperloop is eco-friendly. Since it does not use any fuel for powering its system and works on the concept of magnetic levitation, it is the most eco-friendly solution that's available in the market. Also, solar panels are mounted on the tube in order to ensure that the system is up and running continuously. Now let's look at the energy consumption of all the vehicles in the United States for the year 2017. If you look at the pie chart in the figure, we see that most of the people, or let's say most of the vehicles here, use gasoline and its distillates for its modes of transportation in order to ensure that the vehicle is up and running, which is nothing but 55% of them use gasoline and 22% of them use distillates, which is almost equivalent to 80% of the population of the entire country only surviving on fuels in order to ensure that their mode of transportation is up and running for the day, which is an increasingly and alarmingly large amount of people. What's the impact of doing this? A lot of carbon emissions are emitted into the environment, which leads to air pollution and thereby aids to global warming. It is in need of the hour to have a cleaner mode of transportation for the future. And this is exactly what Hyperloop claims. We need to consider the energy consumption for designing a transportation mode in order to ensure that it does not impact the environment and complies by nature as well. As mentioned in the previous slide, Hyperloop works on the concept of magnetic levitation, and it does not use any fuel in order to power the entire system. Further on, it uses solar energy, which is nothing but a renewable source of energy, which uses its energy, stores it, and consumes it for the entire day in order to operate the tubes, the capsules, and the accelerators that are present inside the system. Thus, Hyperloop is one of the cleanest mode of transportation that is available. I do agree that in case of an emergency, braking is going to be required within the Hyperloop. And we do have motors that will trigger this mechanical braking system. And these motors will be powered by fuels. However, this would occur in case of an extreme scenario and not on a day-to-day basis, unlike the other modes of transportation that rely on fuels on a daily basis for commutation. Thus, as we saw in all of the previous slides before, Hyperloop has numerous advantages associated with itself, be it in terms of efficiency, cost effectiveness, robustness, durability, as well as being environment friendly. Thus, it is the next big thing that's out in the market. Compared to the current modes of transportation that lack certain amount of things, which Hyperloop claims it's going to satisfy, it is the need of the hour to develop such a model of transportation. Before looking at how our current system or my proposed model, Hyperloop, works, let's look at the history of ideas that were existing before this model was proposed. It seems that Musk was not the first person to think about air pressure based transportation. This idea was already carved out in the late 17th century with the invention of the artificial vacuum, which led to the development of the underground transit system using pneumatic tubes for transportation. In the year 1879, the inventor George Medhurst came up with the idea that passenger carriages can be transported from one location to another using pneumatic tubes. And in the year 1812, in London, as you can look at the picture, he developed this station called the Brunel Jolie Sailor and Pumping Railway Station, which was responsible for transporting passenger carriages from one destination to another. It was observed that in the year 1850s or in the mid 1850s, a large number of cities adopted this concept of underground railway transit system with the use of pneumatic tubes. It was forever convenient as the system is going to be underground and it won't involve construction cost or blocking of roads above the ground level. Similarly, there was a London pneumatic dispatch system which was developed. This dispatch system was developed in order to transport goods from one location to another. However, people suddenly realized that this dispatch system can be used for transporting people as well because it's extremely huge from one location to another. In the year 1865, the Duke of Buckingham himself was inside the dispatch system that transported him from one place to another. As you can see in the picture, that's a London pneumatic dispatch system. There is the Duke of Buckingham in the right hand side who is traveling within it to go from one location to another. The current slide is that of the Beach Pneumatic Transit System, which is based here in Manhattan. It was designed and developed by Alfred Elliott Beach, who is a designer, and this consisted of only one stop and one shuttle. But it used the concept of compressed air in order to move the shuttle. It operated in Manhattan between the years 1870 and 1873. It's still present, but not completely intact. However, it's visible to all the commuters or tourists who come and want to visit the beach pneumatic transit system here in Manhattan. In the year 1910, another scientist named Robert Goddard theoretically designed a train that will travel inside a vacuum tunnel. As you can see in the image, there's a sealed vacuum tunnel which is used to transport a train within the tunnel. He claimed that people can travel from New York to Boston in around 15 or 20 minutes via the solution. This was just a proposed idea, it was never implemented. However, it used a concept of vacuum inside a tunnel as well as pneumatic underground transit system. If you look at the next slide, in the early 1990s as well, there were researchers at MIT who designed a vacuum tube that runs on a magnetic track. They estimated that this vacuum tube can travel from New York to Boston in around 45 minutes. In the year 2000, Hyperloop's closest sibling, ET3, came into picture. As you can see in the image, it consists of a car-sized capsule or a passenger vehicle that runs inside a tube which is around 5 feet in diameter, which runs on a frictionless magnetic levitation surface. The linear accelerators which are present beneath the tube, along with the low aerodynamic friction that's present inside the tube, will ensure that the capsule moves forwards. There are also airlocks and air gaps present at the stations in order to ensure that the motion of the capsule inside the tube is smooth and without any pressure on the passengers present inside the capsule. The final proposed idea was that of the food tunnel system in the United Kingdom. This idea was proposed in the year 2010, which was an underground system based in the United Kingdom in order to transport the food from one location to another. It was just a proposed idea and it was never implemented. However, it is somewhat similar to the pneumatic transit systems that are present underground. Instead of transporting passengers, it is used to transport your canisters of food. Later in the year 2003, Elon Musk published his white paper about his idea of Hyperloop. He claimed that around 28 people can travel in a capsule, which is shown in the figure there, and claims that this capsule can travel from New York to Washington, D.C., and ensure that the passengers reach in about 29 minutes. Now, since we spoke about the history of the Hyperloop, let's look at the conceptual system level design for designing the Hyperloop. The Hyperloop consists of four functional systems. As you can see in the figure, the first one is a drivetrain system. This is nothing but the capsule which contains all the passengers, in which contains the interior and the seating where the passengers can sit inside the Hyperloop. The second is that of an electrical system, which consists of various audio devices, your input and your output signals. Your second one was the electrical system, which consisted of three components. The other one is the propulsion system. This system ensures that your capsules, which are present inside your tube, move in a forward direction. It makes use of your accelerators and the concept of magnetic levitation. Your last system is that of a transport system. This system is nothing but your tubes, which contain your capsules and move it in a forward direction. These tubes are huge and need to be erected over a larger area and need to ensure that they are durable and reliable as well. Thus, your entire Hyperloop model consists of your four systems. Each of these four systems consists of the individual components. Let's look at the mechanical components of your drivetrain capsule system. Your capsule system will consist of compressors, your power system, your air conditioning, and your coolants. Your electrical system consists of your electro-optical components, which are nothing but your display devices, your input signals, and your output signals. It consists of software components that makes use of GPS for navigation as well as providing navigational aid, your audio devices, which passengers can hear inside the capsule when they're traveling to understand about directions, as well as your electrical components, which is nothing but air conditioning, heating, and lighting. The next one is a propulsion system, which consists of two components, your electrical component and your mechanical component. The electrical component are nothing but your semiconductor switches. These switches are used to power your capsule present on a particular track within your tube and your solar power cells as well, which are mounted on your tube in order to power them and provide energy to the system. The next is the mechanical component, which consists of your linear accelerators. These accelerators ensure that your capsule moves swiftly inside the tube from one location to another. We will discuss further about rotors and stators when we discuss about the propulsion system. The last one is the transport system, the tubes. The tubes are erected by using huge pylons and steel tubes to ensure the safety of the passengers as well as ensure that the system behaves well in case of a catastrophe or an unwanted scenario. Let us now have a look at the first functional system, which is nothing but the drivetrain system. This is your capsule, which is present in the Hyperloop model of transportation. This capsule is used so that passengers can sit within it and it's safe and travels at a very high speed. There are two proposed types of capsule that have been proposed by Hyperloop. The first one is the Hyperloop passenger capsule, and the second one is the Hyperloop passenger vehicle capsule. What is the difference between both of them? The first one will only transport your passengers, and the second one will transport your passengers along with your vehicles. In case of a Hyperloop passenger capsule, let's say you are during a rush hour. The minimum or the least amount of people that can travel in a Hyperloop passenger capsule are around 28 people. Let's say during rush hour there are going to be 840 people that are going to travel in one capsule. Thus, in order to think about density and number of people that stay in a crowded area, we will need around 40 such Hyperloop passenger capsules to travel. Also, let's talk about the air pressure that's present inside the capsule. How does this capsule move at such a high speed? It is similar to the concept of your aeroplanes. When an aeroplane is descending or ascending at a higher altitude, it's present in a low pressure environment. This low pressure environment ensures that there is very minimum drag and it moves at a faster speed. Similarly, the capsules will be present inside a tube which is maintained at a really low air pressure. However, one thing that we can notice here is that it is completely impossible to have zero vacuum or no air pressure possible. This needs to be addressed as well as when we are near cities, we can't have the capsule moving at an extremely high speed and we need to lower the speed during such scenarios. This is one of the aerodynamic challenge that is present for a capsule as when it nears small cities or big cities. Let us now look at the model of a drivetrain system. It consists of five important aspects. The initial one is the front section, which is nothing but the inlet. The second one is a compressor. The third one, which you can see in the middle, is nothing but the seating area. The fourth one is nothing but the suspension, which is beneath the capsule. You can see it's down. And the last section is nothing but the batteries, which is at the utmost right hand side. So, what makes a compressor or what makes a capsule such fast and efficient mode of transportation is by ensuring that the frontal section of the capsule is minimized. So, as you can see, the frontal section of the capsule is narrow and it's minimized. And how does this work basically? So, when your capsule is running at a very high speed inside a narrow path or a tunnel, any ingesting air that comes will be ingested by a compressor fan and it ensures that there is minimum drag or pressure that's present and travels at a higher speed. Also, the justification for why a compressor fan is used inside a capsule will be mentioned in a short while. If you see, there are seatings that are present in the middle section. These seatings are designed in such a way that even during a high speed transportation, the comfort of your passengers will always be met. At the same time, you can see suspension and batteries in the end section. Now let us discuss as to why do we use a compression fan and a compression motor in the frontal section. Whenever you're traveling in a narrow path, there will be air that is going to be present beneath your tube walls and your capsule. This air will be sucked in by a compressor fan and will then be compressed by a compressor motor and provided to your air bearings for the suspension or the support of the system. As you can see, you can have suspension system which is present in the bottom. What is the use of the suspension system is quite clear. In case, since a capsule travels within your tube, In case the distance between your tube and your capsule reduces, the pressure in the air bearings that are present inside the suspension system will be increased, which will move the capsule away from the tube. So imagine if this is a capsule and this is your tube surface, and a capsule is moving inside your tube. Just in case the distance between your capsule and your tube is reduced, the bearings in your suspension system will ensure that the pressure is increased and the capsule is then restored in a normal direction and a capsule moves forward inside a tube. So it's like ensuring that the distance is proper so that there's no collision as such. And then you have your batteries in the end. These batteries are used to provide cooling or ensure that power is operating, the compressor motor is operating, as well as the AC and the heating within a capsule is maintained overall. So this is nothing but how a capsule works. And this is the most efficient design of capsule possible. You need to always ensure that the frontal area is minimized so that it can navigate at a really high speed. If you look at the bullet trains in Japan or any fast moving mode of transportation, the frontal area or the design in such models, the frontal area is always minimum or towards a pointy edge, so that when it's traveling at a really high speed and cutting through air, the amount of air pressure or the air that's released in a low pressure environment can be minimized by using a compression motor and can be used for supporting the entire vehicle. And that's the same concept that is being used for a capsule drivetrain system here. If you look at the other slide, this is nothing but the interior of the capsule, which is designed in such a way that the comfort of the passengers is always met. So when I mentioned about the suspension system, in case there is the distance between your capsule and your tube is reduced, in order to avoid the effect of going back to the same direction, there'll be deployable wheels that will be attached within your or beneath your capsule. These deployable wheels are similar to that used in aeroplanes when you're descending from your flight. The deployable wheels are produced out so that the pressure felt by the people is completely irrelevant or not a high impact one. Thus ensures that your comfort of passengers is met during the time of a high speed transportation. Now let's discuss about the propulsion system. The propulsion system is responsible for transporting the capsule from one destination to another inside a tube. There are four stages in a propulsion system. The first stage is when the capsule needs to move from a speed of 0 to 300 miles per hour when it takes off from a particular destination or a source. The second mode is to keep the speed of 300 miles per hour in case of an ascent. The third one is to increase the speed from 300 to 760 miles per hour for the high speed transportation. And the fourth mode is to reduce the speed from 760 to 300 to 0 miles per hour when it reaches a particular destination, which is called a deacceleration. So, how does it achieve this acceleration and deacceleration? Is via the use of linear accelerators. And again, the question arises as to why do we use a linear accelerator? The first reason is because these accelerators ensure that the capsules are lightweight, it caters to smaller dimensions of the capsules, and also ensures that the production cost is low. So if you see in the diagram currently, we use two kind of linear motors. One is for the outgoing train and one is for the incoming train. And these are then backed up by switches. These are nothing but semiconductor switches. And these switches are then backed up to solar power cells. The question arises as to why do we use these switches? Because we're being energy efficient here. You will only power that part of the track where the capsule is currently moving. So only the solar cells that are belonging to that part of the track where the capsule is currently moving will be used, and hence we use semiconductor switches for it, which is a very clever and a cost efficient trick for saving your energy as well. Let's look at the interior working of your linear accelerator. It consists of two such things. One is your rotor, which is mounted on the capsule. Then there's a starter, which is mounted below the capsule. And the trains run between these motors and starters. There's an air gap, as you can see, between both of them, which induces your electromagnetic induction, which further on releases or produces your magnetic levitation. Let's talk about the third system, which is nothing but the tube system. The tube system is used to contain your capsules. It is claimed that the pressure inside the tube system will be one-sixth to that of the pressure present on Mars. In order to ensure that your tubes are mounted correctly above the ground level, we have two structures within your tube. One is that of your pylons and one is that of your tubes. Your pylons, as you can see, are on the upper side and the tubes which are below. They are constructed in such a way to ensure the thermal expansion factor of the tubes as well. In case of an extremely hot environment or heating conditions, these tubes can expand and that needs to be taken into picture. Hence, the pylons should be constructed in a cost efficient and an optimal way as well. As you see in the next slide, this is a proposed model for your pylon along with your tube construction for the Hyperloop. We discussed about the analysis and the design of your function system and the components. Let's talk about the production cost for Hyperloop. The cost for Hyperloop depends upon the three most important functional systems of the Hyperloop: the cost of a drivetrain system, your tube system, as well as your propulsion system. Among the three of them, the tube system is the one that costs a lot because you're supposed to have an engineering marvel in order to ensure that the tubes are placed properly above the ground level, taking all factors into consideration, which gives it around 4.6 billion USD cost. That for your drivetrain system is 54 million USDs, and 350 million USD is associated for your propulsion system, which ensures that the cost of your entire Hyperloop model is going to be around 6 billion USD dollars. Let's look at the cost of a propulsion system. In a propulsion system, majority of the cost is associated with your starters, which will be mounted below the tube. Your power electronics compound to a minimum of 33%, which is used for giving battery backup, as well as semiconductor switches for switching and ensuring only particular part of the track is being charged, and your energy storage, which is nothing but solar power cells. As you remember, there were rotors that were also being used in your propulsion system. However, the cost is minimal and doesn't amount to a lot. Now let's talk about the reliability and the robustness of the system, which is extremely important for analyzing our system. Let's say we talk about capsule depressurization. In such a scenario, the air pressure in the capsule will be lowered. However, the onboard environmental system will ensure that the pressure inside a capsule is still maintained to the optimal power. In case of a worst case scenario, similar to that of an aeroplane, a deployable oxygen mask will be given to the passengers and that can ensure that the pressure in the capsule has been maintained. Your system should always be resilient to anomalous weather conditions such as that of an earthquake, and the tubes and the pylons as well as the capsules have been designed in such a way. In case of a power outage, which is a rare scenario since your capsules and your entire system is being powered by solar battery cells, there will be mechanical brakes that will be triggered in case a power outage occurs and the capsules will be brought to a halt inside a tube. An interesting case is that when a capsule gets stranded inside a tube, let's say we have 40 capsules and the 19th capsule gets stranded. All the capsules that are ahead of the 19th capsule, number 1 to 19, can move forward and reach a destination. The one that is stranded will be stranded, and the ones after 19 to 14 can trigger the mechanical brakes and be brought to a halt. This 19th capsule is then moved forward with an electronic motor and taken out for service, and the capsules from 1 to 18 and 18 to 14 are joined again and can move forward to the particular destination. This ensures that the integrity of the system, which is completely important when you're designing a system, is well maintained, and Hyperloop complies by this. Now let's look at the design for your system development test configuration. This is responsible for ensuring that your system as a whole has been tested. Since my Hyperloop consists of four functional systems, working of all these systems together for checking the entirety, the completeness, and the integrity of the system is extremely important. So we give it different kinds of inputs. The first are the basic operational inputs, which include your passengers and your luggage inside a capsule, the navigation aid, your propulsion system, and your electromagnetic levitation as well. The other two kinds of inputs are used to test in case of emergency. So checking your onboard passenger emergency, what happens in case of disasters like earthquakes, or is the system resilient or durable enough? And the output of your system development test configuration should be your passengers and luggage being transported from one destination to another in a proper way. So testing with these various kinds of inputs gives you a bigger picture and a thorough and a complete analysis of the working of your system. The next slide that we talk about is a transport route, which is extremely important for our model since it's a transportation based model. As you can see in the picture, Hyperloop is going to commute from San Francisco to Los Angeles. The reason why these two routes were selected was because they're one of the most crowded and the most populous cities in the state of California, and daily commuters travel from this location to another either via various modes of transportation. So this is the speed that's being shown and the breakup of the speed for your Hyperloop. From Los Angeles, we're going to have two sections, the south section and the north section. The speed is going to be maintained to 300 to 555 miles per hour. The IFI section, which is a direct stretch, which contains very minimum bend radii. Bend radii is the section wherein there are no bends across your road, so you can travel in a straight line and there won't be any need to reduce your speed of your capsule inside the tube. Hence, the speed here is maintained to 760 miles per hour, and the end, your destination, it reduces to 300 miles per hour. The total time is nothing but 35 minutes. This is something which is suggested transport route that you can see, which includes additional cities which have been decided based upon their population density. The last point of this presentation is discussing the challenges associated with Hyperloop. I have identified four such challenges. The first one is that of robustness. How robust is my system? We claim that the capsule that is present inside the tube runs at an extremely high speed. But however, we also discussed that there are going to be existing bend radii which will be present within your transport route. As we discussed in the previous slide, bend radii are places where the speed of your tube or your capsule or a train should reduce from 760 miles per hour to 300 miles per hour. And to switch from such a high speed to a low speed, we're going to make use of semiconductor switches. Solely relying on the concept of semiconductor switches in order to make the switch from such a high speed to a low speed seems like an impractical but not an infeasible idea. However, this needs to be tested really well in order to ensure the system is robust enough. The second point is that of complexity. How complex is my system? We have designed the system in order to ensure that there's going to be lower dynamic friction and the capsule moves at a really high speed. Also, when the tubes will be placed on the pylons, we need to ensure that the thermal expansion factor of the tubes need to be taken into consideration. However, designing such pylons that cater to such specific thermal expansion is a complex task in itself, and such issues need to be addressed at an early stage of development or concept initialization stage as well. The third challenge is that of reasonableness. As it was claimed by Musk and their engineers, the Hyperloop will attain a speed of 760 miles per hour. However, during the first testing last year in 2017, it achieved a speed of only 70 miles per hour, which is extremely less compared to what they claim. They, however, claim that they say they're going to achieve a speed of 260 miles or 300 miles per hour. And Musk also tweeted that it can go at a speed of sound. However, before making such statements, the technical and the physical constraints of the system need to be analyzed thoroughly. The last challenge is that of reliability. How reliable is my system in terms of a disaster or an earthquake? Also, since it uses aerodynamic friction or low aerodynamic friction in order to travel at a really high speed, when it has to achieve a lower speed in case of a disaster, will the motors have sufficient power to switch from a high speed to a low speed? Is something that determines the reliability of a system and needs to be assessed thoroughly as well. I would like to end my presentation, and I would. It was an extremely thorough engineering analysis that I did of Hyperloop that I extremely enjoyed a lot, and I hope you all gained some knowledge from it as well. So thank you.